Thank you. On behalf of my team members from City University of Hong Kong and Hong Kong University and some overseas partners, I'm pleased to present our major findings in this CRF TRS projects entitled A Comeback System for Terahertz Imaging and Spectroscopy. Now, terahertz frequency is the, between the millimeter wave and the optical frequencies. And it is typically now defined the 100 gigahertz to 10 terahertz as the terahertz gaps. As the developments of this frequency range is not as well established as its electronic and photonic counterparts. And the very expensive testing equipment actually impede the development of these frequency regions. Now, this is the terahertz imaging and spectroscopy system at the onset of our projects. Okay, you can see that this is a frequency domain system, and we have a network analyzers here, and then a pair of this frequency extender. In this particular setup, the frequency range of this is 220 gigahertz to 325 gigahertz. And each pair of this module will cost 2 million Hong Kong dollars. So if we were to complete the frequency range from 0.1 terahertz to 1 terahertz, it will cost 10 million Hong Kong dollars. Okay? And similarly, this is a time domain systems. Okay? Again, they are bulky, low output power. And in terms of the imaging, the scanning is a mechanical raster scanning, so it is rather slow. Okay? And we also need to build a customized components in order to enhance the image quality by exploiting the polarizations of the wave. So to improve the imaging quality, we can make use of this so-called mirror matrix polarimetry imaging. And you can see that by computing the mirror matrix, we can actually delineate the information of the samples, okay? And each of the pixels of the sample will be characterized by this so-called a 4x4 matrix called the mirror matrix, okay? Now, to exploit the polarimetry effects, we need to have 36 combinations of the polarization of incident wave and the receiver wave, okay? These polarizations include horizontal, vertical, 45-degree, and minus 45-degree, left-hand and right-hand circular polarizations, okay? And each of the pixels, we will compute the mirror matrix. And from the mirror matrix, we can actually compute further information. For example, this one is an optical mirror polarimetry for tissue diagnosis. And basically, this is the human cervical tissue with precancers. Okay, you can see that if we do not exploit the polarization effect, you can actually cannot distinguish the precancer region as well as the normal region. Whereas if we make use of this mirror matrix and compute the depolarization and retardance from this mirror matrix, you can actually distinguish the two regions very clearly. But this is done in optical frequency. So when we construct the mirror matrix imagery at the terahertz frequency, and in this particular case, it is the transmission mode imaging a piece of leaves. And it turns out that the goodness of the image is actually predicted by this so-called similarity. This is SSIM analysis. If this number is closer to 1, that means the quality of the image is good. But you can see that whether it is mirror matrix or the normal polarimetry image, they are similar. So in this particular example, the mirror matrix is not as crucial, okay? Whereas this is a reflection mode, and you can see that this target is make use of this ITO with a different width of the strips. And by making use of the mirror matrix, you can see that we can have a better quality of the image. In particular, you can see that we can actually identify this region much better, as well as we can have sub-wavelength imaging, because the width of this particular strip is actually only half of a wavelength. If you can excuse me, I just take off my mask. I cannot breathe. I'm sorry. Okay, because we need to have a different polarization, and they are not commercially available, so we have to design and fabricate lenses with different characteristics, okay, using 3D printing. So you can see that this is a linear polarized far-field lens, whereas this is a circular polarized far-field lens, and these are the focusing lens. By changing the thickness of the pixel, we can actually manipulate the phase information of the aperture there. From there, we can determine what kinds of performance we need. So, for example, this one is a focusing lens, okay, so that we can focus the energy to the objects under test. And here we can show that it is we have made use of a doublet of these lenses. You can generate bezel beam that can actually steer to different directions, okay, depending on the rotations of these two lenses. Now, the advantage of this bezel beam is that when the wave propagates, it will not diverge. Okay, it's a non-divergent beam. Okay, so that the energy can be actually remain more or less constant along this direction. Okay, as opposed to some far-field lens that the energy will be actually rapidly decreasing due to the inverse square law. Okay, and this one actually can generate different OAM mode, orbital angular momentum. Okay, that means we can have more information from the target if we make use of these kind of lenses. And in this particular one, we can combine the two features here to generate a bezel beam with a different orbital angular momentum index, so that we can also change the range that the field remain basically constant. Okay. Now we can also do the multiplexings of different OAM mode, and this one is actually the regular OAM mode. Then it will diverge, whereas we can change the metal surface lens so that the surface range of this beam will remain constant in this region. Okay. Now this is only done in millimeter wave because no teams in the world can afford to have two sets of this very expensive TRS equipment. Now this one, you can see that the reflector of this is that when the beam come in, it will focus the energy at the focal point. Okay. When we change the frequency, actually we can have a linear translation of the focal point. Whereas this reflector will actually provide two-dimensional changing of the focusing beam. Okay. However, you can also see that when we scan along this direction, the shape of the focal point actually distorted, and we have to do more optimization to actually minimize such a distortion. Now, the reason why we want to do this kind of reflector is that we want to get rid of the mechanical scanning so that we can do the beam scanning much faster electronically. Okay, now, in order to focus the energy more in a certain directions, okay, we design this terahertz antenna. It has a very high gain of 33.4 dBi, okay, using the micro-machining technology. On the other hand, here we also design other antenna such that the antenna beam will actually change its direction when we change with the frequency. Okay, it can provide some frequency scanning. Okay, whereas this goblet line antenna here will have very wide band, operating from 350 gigahertz all the way to 500 gigahertz. Now, once these antennas are fabricated, we cannot manipulate the characteristic of the beam, except using frequency scanning for the direction. Here we have fabricated other terahertz devices. For example, these are the passive polarizers. Okay, depending on the operating frequency, it has different performance. The key thing about this work is that we measure the goodness of the circular polarization. You can see that at very high frequency of 900 gigahertz, the measurement and simulations are overlap. Okay, it's very difficult to perform the measurements here. Whereas this is an active terahertz polarizer, okay, and we make use of the radium dioxide, VO2, and by applying a voltage there, we can actually turn on and turn off the transmission of a particular polarizations. This one is a hologram that we designed so that when it is illuminated with a terahertz frequency, it will display an image of terahertz. Basically, this is the acronym of the word terahertz. Okay, now we have also conducted the time domain imaging using our time domain spectrometer. Now, if we do some signal processing such that we can actually shift the onsets of the beam, you can see that we can actually construct three-dimensional image of this structure here, which is a 3D printed plate with hollow tubing inside. So you can see that we have three-dimensional display of this. Two of the dimensions are spatial, and the third dimension is actually temporal. Okay, so that we can have a three-dimensional display of the object. Now here is the multispectral imaging of a zebrafish. At lower frequency of 100 gigahertz, you don't see, actually the resolution is not good enough for us to see the image of the fish. When the frequency continues to increase, then you can see the shape of the fish as well as more detail of the internal feature of the zebrafish. Oh. Okay. Now, it turns out that making use of the time domain spectrometer, actually we can have phase information from the data that we measure. And it turns out that if we want to have other combination, they can be computed by the two different polarization, the 45-degree and the minus 45-degree. And based on the information and phase information, we can actually compute all the other measurement data. And because they are in 45-degree and minus 45-degree, we need to have a polarizer that is very wide band that will work from 1 terahertz all the way to 1 terahertz. And it is the constructed mirror matrix image, and it is the further decomposition of the mirror matrix, and you can see that we can have very fine detail of the leaf, okay, at different frequency. And we can also make use of the time domain spectrometer to do the spectroscopy, and here we can basically measure different material, okay, that we commonly use for our terahertz devices, and then we can extract the dielectric constant as well as the loss tangent of different materials. And here we show the terahertz spectroscopy for cancer diagnosis, and here we can have the reference is just the polyethylene pellet, and then we put the cancer cell with it, and then we measure the samples with the cancer cell incubated with different complexes, and we can see that by incubating the cancer cell with these complexes, we see the extra resonance, okay, from the spectrum of the sample. And in order to improve the efficiency of the conversions from the optical frequency to terahertz frequency, we design photoconductive antenna. Okay, here we make use of the gallium arsenide lanthanide wire, okay, together with the low temperature gallium arsenide substrate. With and without the lanthanide wire, we can see that the signal intensities are different, and we can see that with the use of the lanthanide wire, the frequency output, the output will be higher than without using it. And in this particular slide, we compare with the commercial photoconductive antenna and those with our lanthanide wire, and you can see that we make use of the actually very cheap substrate without the low temperature gallium arsenide. The output with the lanthanide wire is actually comparable to the commercial photoconductive antenna. And in order to generate the circular polarization that we may need, so we also design very wideband circular polarizations polarizer here. And you can see that the experimental results and the simulations compare very well. Now, we want to provide electronic beam steering, okay? So here we show a IC that we have designed, okay, that operate at 320 gigahertz so that it can provide electronic beam steering, and it can go from minus 30 degree to positive 30 degree, and we make use of a microstrip patch antenna with cavity backing. And the output of this IC, however, is very small. It only has 16 microwatt. Okay? We hope to increase the output power. And this is the design of our IC working at 482 gigahertz. And you can see that it is a 2x2 array. And it has an output power of 162 megawatt. Basically, it is 10 times the output power of the previous design. And next, we designed a 4x4 radiator IC. And you can see that by carefully placing the slot antenna element to reduce the backscattering as well as the generations of the surface wave, we can see that we can have the IC radiating, and then we place an expensive Teflon lens, which actually was fabricated in Shenzhen, okay, through Taobao, okay, and it only costs about 500 RMB, then several thousand US$ silicon lens used by other people, and we can actually generate a record high of close to actually 29 dBm EIRP, and EIRP is an effective isotropic radiation power, which is actually a measure of how far, how long a distance we can propagate the terahertz. And the output power here now increased to 2.4 dBm, which is translated to 570 megawatt or 0.57 milliwatt. So we continue to extend our terahertz source, and it is 700 gigahertz, which make use of the third harmonic. And again, we design our IC such that it gets the highest output power for the frequency beyond 600 gigahertz. Okay? And the power here is also 0.57 milliwatt, but at a much higher frequency. So it is very difficult to do. And it is another IC that we have designed, making use of our specialties in antenna design. By making use of this particular antenna design, we can reduce the size by 1/3 of the antenna, and then we can actually improve the radiation efficiency from 31% to 69%. Now, because we can reduce the size of the antenna, we can actually reduce the overall size of the array, okay? So that we can have the highest output power per area, for chip area, okay, using this 65 nanometer technology. Now, this is our newest design, operating at 640 gigahertz to 690 gigahertz. We have about 50 gigahertz of tuning range. And you can see that this has 144 elements, much bigger than what we have showed you earlier. And you can see that it is the output of the array. And in fact, we can change the biasing voltage, and we can tune the directions of the beam. We have a tuning range of minus 40 to 40 degrees. Okay? Now, our output power of this IC is 8.1 milliwatt. This is a commercial and expensive terahertz extender. Its output is only 5 microwatt. So our output is 1,600 times that of the commercial and expensive terahertz frequency extender. Okay? And for the time domain spectrometer, again, the output power is very low. Okay? So because we have a very high power IC designer, we can replace this module, this bulky transmitter by our tiny chip. Okay? We make use of the lens so that we can perform the same imaging. Now, here we show the imaging of the leaf. You can see that the detail of the leaf is much better than the previous one I showed you because the power of our IC is actually much higher than the commercial equipment. Here, we don't even need to make use of the mirror matrix computation because the dynamic range of the system is much better. Okay? And so we also make use of the TRS imagings of the other samples. Okay? This is the dental floss, paper clip, and the knife. And then they will mount it on a thick cardboard paper. And then we do the imaging. And it is at the spatial resolution is 1 millimeter. It is 0.5 millimeter. So you can see that for this dental floor here, maybe you cannot see it very clearly, but you can see that actually there's some indentation here. Okay? But if you look at the image, we can actually display that indentation very clearly, okay, from our image because of the high power of our source. Okay? And if we basically pick the range of the display of the images by selecting the scale, we can actually look at these images quite differently. Okay? Now, we have shown you the source. Okay? Now we're showing you the receiver. Okay? This is a 540 gigahertz receiver with the third order subharmonic mixer. And you can see that actually our noise figure as well as the conversion gain is actually much better than the other designs. Okay? I just don't have the space to show you the comparison table. And here we make use of our detector, okay, and to monitor the drying process of a thin wet cloth. Okay, you can see that as times go on, the water actually evaporated, and then you can see the transmission of the TRS frequency with higher transmissions. Okay, basically we can monitor the water content of the target. Okay, now so you can see that if we can actually develop a mixer array, and we have a high power source, we can actually do the imaging very rapidly. Okay, now you may ask, well, how come the frequency are not the same? Although, well, it's supposed to be the same, but in order to generate the publication, we have to choose a frequency that we can publish the paper. Okay, but of course, we can actually make them the same. Now, we told you that once the antenna is fabricated, it's difficult for us to manipulate the radiation property. Now we have demonstrated you a new antenna, metal surface antenna called a space-time coding. Using software, we can control the radiation property of our antenna. Now this is demonstrated at millimeter wave frequency at 27 gigahertz. Okay, the fact is that we use it as a proof of concept, and we are now working on making it into a chip. Okay, the key feature of this metal surface antenna is that we have a metal atom here, which is actually an antenna, a slot antenna, okay, on a waveguide, and then on the aperture of the slot, we have some switches there. Okay, by using an FPGA, we can turn on and off the switches. Okay, so this is we have 82 radiating element there, so you can see this is a spatial control when we could turn on each of the switch, and it is in the duration where we turn it on and where we turn it off. And by having a different so-called space-time coding matrix, we can actually steer the beam in different direction. And the frequency of this radiation actually is different from the input frequency. Okay, we can make it the same. We can make the harmonic frequency radiating. Now, this is actually a modulations of the idea is based on an invention that we make on so-called the amplitude modulated liquid wave antenna. We actually modulate the physical aperture of the antenna, okay? But by making use of this space-time coding, we mimic the modulation, the spatial modulation, but we use a software to control okay, the biasing of the matrices so that we can have a different radiation at different direction. Okay, we can also have several beams simultaneously because the coding itself is linear, so we can superimpose the different coding matrices to bias the switches so that we can simultaneously to have the free beam in different directions, same directions, okay? And they can be of the same frequency and different frequency. So this is a recent paper we published at Nature Electronics. Okay, so what we actually had improved in the subsequent work is that we can also change the polarizations of our radiation. So each typical electromagnetic propagation will have 5 parameters: the polarization, amplitude, frequency, direction, and phase. Our single antenna can control all of these 5 parameters, okay? Use the software control. Now, because we can control the aperture, phase, and amplitude distribution, we can focus the beam, we can have a linear translation of the focal spot, as well as along the same direction. So basically, we can manipulate the beam propagation property to enhance the imaging system, okay? So now we have demonstrated to you that we have developed many enabling technology for a compact system for terahertz imaging and spectroscopy through the development of high-power terahertz source in frequency domain, as well as enhancing the efficiency of the time domain terahertz generations. And we also developed high-gain terahertz antenna to make the beam very narrow, and we can replace the feed of this bulky waveguide by our chip so that the whole antenna can be basically make compact. We also show you how to make use of the metal lens, develop metal lens for the wave manipulation, use 3D printing. And we also introduced a new idea of the beam steering devices. At this point, it is operating at millimeter wave, and we are in the process of developing the IC version of this groundbreaking antenna design for imaging. And I know that my time is almost up. So on behalf of our team, we would like to thank the Hong Kong Research Grant Council for the support of this research work through the frame-based research scheme. Thank you.
Thank you, Professor Chan. If you have any questions for Professor Chan, please raise your hand and let us know. We will then hand you a microphone so that you can also ask your question.
Professor Chan, very nice work. Thank you so much. One thing I'm interested in is your 3D printed lens surface. And as we know, for 3D printing, the surface roughness and the step features could be mitigated. Depends also your material and process techniques. So I was wondering, what's your thought whether you can take advantage of the 3D printed surface for the purpose that you are doing to tune it?
Okay, now as you can see that we designed our lenses, okay, with 3D printing, and in order to generate the circular polarization, we have special feature at the bottom of these 3D lenses, okay, that we have a grating there, a so-called dielectric grating. It is actually very interesting. I'm glad that you asked. This 3D printer is very inexpensive, only $5K US. The manufacturer of this printer actually suggests its customer to print the structure in this fashion so that they can have a supporting struts to support the structure. But if we do that, our lens will be distorted. The quality is terrible. It doesn't work. So what we did is that we print it like this, okay? But we have a lot of very thin, like hairy type of supporting structure that can be detached from the plating platform very easily. And then we can actually use a brush to take off these struts. So therefore, the manufacturer was so surprised that we can have this lens operating at 300 gigahertz. So this is from 3D Form Lab, okay? And that material is some thermal type that can withstand high temperature. It is on their you can go to their company and you'll find that material, okay? And it turns out they invited us to their exhibition to share with their customer what kind of things that we can do. But we limited the frequency, operating frequency to 300 gigahertz. Beyond that, the resolution of that 3D printer is not good enough. Okay, but for any lenses working below 300 gigahertz, it will work perfectly. Yeah, thank you.
Do you have other questions? Yes, please.
So you mentioned early on the use for biomedical scanning or imaging. You have any success in the application in those areas?
Some. Okay, let me explain. If we want to distinguish certain specimens that are cancerous or not, yes, we can distinguish them very easily. The fact is that if they are cancerous, when they make use of, in fact, Nikki is there here, Dr. Nikki is here. She prepared the sample for us. It turns out when they dry off the process, the water content actually disappear and leave a lot of bubbles or air bubble there. So the absorptions of the TRS actually is smaller. So we have better transmission. That is very successful. But on the other hand, she prepared some of the sample with a thicker specimen. The power of our old, our commercial equipment is not sufficient for us to look at the image very in detail. But now we have our own high power source. We should be able to get better image of a thicker substrate, specimen. Yeah.
Another question I'd like to ask is you said your scanning range is -40 to 40.
Yeah.
What limits you? Because it looks like you can scan -90 to 90, but you're saying...
Well, typically for the antenna guy,
yeah.
The scanning from the main beam to, let's say if it is less than 5 dB, we stop there.
Okay.
Although you can see that, yes, we can go further. Because the power is high, in fact, we can scan higher. Yeah. So, in fact, we are now working on the imaging system that if we scan, okay, we don't need to have the sample to move. And we can actually compute the image very easily. We are in the process of doing that, yes.
Okay, thank you.
Thank you.
If you have further questions, please raise your hand to let us know. Then maybe I have a quick question. So I'm not an expert in any of those areas. I'm just wondering, for my daily life, are there any applications that you have developed or that come directly there from? So I saw, for example, you showed a laptop or also a DVD. So how would it change my everyday life?
Okay. Now, although I only show you the use of some of our results for imaging, but for example, this IC, okay, if we incorporate the baseband there, we can use it for communications. For example, in the future 6G wireless communication, one important element is not just communication, but also sensing. Imagine that if your mobile phone has one of these chips that can allow the beam to scan and sense the environment and provide you additional information. Okay, this is one of the future applications of this high-frequency devices. But I show you that because of the high output of our IC, not only that it's very small, it generates a high-powered, much higher, 1,600 times of the commercial equipment, very expensive equipment. So we can actually speed up the development, R&D, of terahertz research through the availability of this high power source.
Thank you, Professor Chan.
Thank you.
Do we have further questions from the audience? Then thank you, Professor Chan.
Okay, thank you. Thank you.